Hello everyone, welcome to the interactive presentation for our paper on modeling attention in human crowds. This is work done with my collaborators Katharina Muelling and Jean O. We are from the Robotics Institute at CMU. Without further ado, let's dive in. Our goal in this work is to enable robots to navigate efficiently in dense human crowds. To achieve this, we need very accurate predictive models for future human trajectories so that the robot can plan paths that are more safe and interpretable for surrounding humans. The main challenge in solving this problem is the complexity of human-human interactions within the crowd. So we need a way to model these interactions while coming up with an accurate predictive model. Our work starts out by testing the hypothesis that humans, while navigating, care only about a subset of their surrounding dynamic agents. Most previous approaches infer this subset using only proximity. But we claim that influence in crowd is not just a function of proximity and that there are other important factors too. These important factors could include velocity, acceleration, heading, etc. In our approach, we use spatiotemporal graphs and recurrent neural networks or RNNs to capture such influences. Spatiotemporal graphs are graphical models that allow you to capture dynamics of a system that evolves both spatially and temporally. The nodes capture dynamics of entities using node RNNs, and the edges capture spatial and temporal interactions between the entities using edge RNNs. The interactions captured by the edges are used in predicting the future trajectory by combining the spatial edge RNN outputs using a soft attention module, which is our main contribution. The soft attention module predicts a distribution over spatial edges at each time step. This captures the importance of each surrounding agent for the agent considered. The advantage of using soft attention is that it is completely differentiable and scales well with the number of agents in the crowd, which could possibly vary with time. In the next few slides, we will go over the results. Quantitative results show that our approach performs the previous state-of-the-art social LSTM on 5 benchmark real-world crowd datasets. We believe our approach works better because our model accounts for more influencing factors than just proximity. To better understand what our model learns, we observe the soft attention output for example scenarios. In the following figures, the red trajectory corresponds to the agent in consideration and the rest of the trajectories correspond to surrounding agents. For any trajectory, the blue diamond corresponds to their current position, dots correspond to their previous position, and the radius of the circle around their current position is proportional to magnitude of their attention weight. Our model learns behaviors such as ignoring stationary pedestrians even in cases when they are close in proximity. Additionally, it learns to give higher importance to surrounding agents moving in the same direction or agents with whom there might be a potential future collision. This illustrates that our model learns to account for factors other than proximity to obtain more accurate and interpretable predictions. I hope this gave you a good overview of our work. For more details, check out the paper and the poster. Thank you for your attention.